In this lesson, we are going to talk about continuity, and a very common way to think about continuity is that you can draw the graph without picking up your pencil. What we've been looking at are limits. And when we're determining the limits, we look at x values that are near a particular number. So we look near particular x values. For continuity, we want to know, here's an example. The limit as x goes to 3 of x squared minus 9 divided by x minus 3 equals 6. Which tells us that when we are near x equals 3, the y values of x squared minus 9 over x minus 3 are really close to 6. Continuity is where we look at what happens at the specific x value, and we look at what happens near the particular x value. So we're doing the limit, and we're looking at the value of our function at that particular place. So here is the definition to say that f is continuous at x equals c. Let f be a function defined near x equals c. We say f is continuous at x equals c if each of the following is true. 1, the limit as x approaches c of f at x equals L, which is the same thing as saying that the limit exists. X equals c is in the domain of our function, and f at c equals the value of the limit. So those three conditions need to be met for us to say that a function is continuous at x equals c. So let's look at that function that we already had before, x squared minus 9 divided by x minus 3. Is it continuous at x equals 3? Well, the main answer is no, because x equals 3 is not in the domain. So that's it. If you don't satisfy all three of the conditions, then you are not continuous. Let's do another example. Same function, f at x equals x squared minus 9 over x minus 3. Is it continuous at x equals 1? Well, I know that the domain, x equals 1, is inside of the domain. Let's look at the limit. Now, in section 1.3, where we did limits analytically, we talked about simplifying our functions by canceling out common factors. So our function f at x equals x plus 3 when x is not equal to 3, because I was able to cancel out the factor of x minus 3 from the numerator and denominator. The limit as x goes to 3 of x plus 3 equals 3 plus 3, which is 6. And we talked about that in section 1.3, finding limits analytically. And x equals 1 is in the domain. And the final thing I need to check is, what is f? I don't know why. I just noticed that I did the wrong limit. I was supposed to be doing x going to 1 of x plus 3, and that equals 4. And f at 1 equals 1 plus 3, which equals 4. And since those two numbers are equal to each other, we are continuous. So the answer is yes, we are continuous at x equals 1. So many of the functions that we are going to look at are continuous for all the x values on their domain, in their domain. One exception is piecewise functions. And so we need to investigate what happens with a piecewise function at the places that we break up the rule, that we change pieces. So let's look at an example. F at x equals 2x plus 5 if x is less than 1, and f at x equals x squared plus 3 if x is greater than or equal to 1. If I do the limit coming in from the left, we get 2 times 1 plus 5, which equals 7. If we come in from limit from the right, we get 1 squared plus 3, and that equals 4. They're not equal, so therefore you can't be continuous. The limit does not exist as x approaches 1 because our one-sided limits are not equal to each other. So let's look at another example. Where is the function square root of x minus 1 plus the square root of 5 minus x continuous? Well, the main thing that we need to do is find the domain. We need x minus 1 to be greater than or equal to 0 and 5 minus x to be greater than or equal to 0. So we need x to be greater than or equal to 1 and x to be less than or equal to 5. This is a compound inequality, 1 less than or equal to x less than or equal to 5. And so my domain is the interval closed from 1 to 5, closed at the end. And f at x is continuous on its entire domain. And here we're going to look at a graph. This was created in Desmos, and we could see that it's continuous everywhere. As mentioned on the first slide, the idea is that you can draw the graph without picking up your pencil. So like in section 1.3 when we talked about limits behaving nicely, continuous functions also have the properties that we would expect. Here is a picture from page 40 in our textbook, Apex. If you add two continuous functions, the sum is a continuous function. If you multiply a continuous function by a constant, we're still continuous. If you multiply continuous functions, we're still continuous. When you divide continuous functions, it's continuous as long as the denominator is not equal to 0. Raising a function to a power, it's still continuous. Taking the nth root of a function, still continuous, as long as we don't have negatives inside of a square root or a fourth root or any even root. And the composition of functions, they are also continuous. They behave exactly as we expect them to. So for our last example, where is the natural log of 1 minus e to the x continuous? And the first thing that we want to do is find the domain. So the domain of y equals the natural log of x is all x greater than 0. The natural log of x is one of our common functions. So we need 1 minus e to the x, the input, or the inside, to be greater than 0. So that means 1 is greater than e to the x. Undoing e to the x by taking the natural log of both sides, we get 0 is bigger than x. So y equals the natural log of 1 minus e to the x is continuous for all x less than 0. And that would be on the interval, in interval notation, negative infinity to 0, parenthesis, because we do not include x equals 0. And that is continuous functions.